Alright, hello, it's Olivia, and I was assigned to page 279, number 80, and page 488, number 39 in our books. And number 39 involves intermolecular forces and figuring out which substance has which intermolecular force. And page 279, number 80, involves calculating the change in enthalpy of 3 different reactions and answering questions on that reaction. So, number 80 states, calculate delta H, which is the change in enthalpy, for each of the reactions. Explain why water or carbon dioxide in an extinguisher might not be effective in putting out a sodium fire. So from this we can infer that water and carbon dioxide will not take a lot of heat out of the reaction, out of the sodium fire, because they will not be effective. And when looking at our 3 given equations, number 1 involving O2 should take a lot of heat out of the reactions. So when looking at our answers, we can infer that O2 in an extinguisher will be a much less number. So in order to calculate delta H, the change in enthalpy, we're going to be using this formula, which involves delta H of products minus delta H of reactants. So, number 1, taking the delta H of each individual molecule and multiplying it by the coefficient on each side, setting it up in the order of our initial equation, multiplying it out, adding it up, and plugging it into this equation. So first off, with 4Na plus O2 yields 2Na2O. Number 2, 2Na plus 2H2O yields 2NaOH plus H2. And number 3, 2Na plus CO2 yields 2Na2O plus CO2. Now we can look at our math. So, dropping down this coefficient and using a table on the side to find the delta H of each individual substance. So for Na it is 0 plus O2, 0, yields, drop down the coefficient, 2 times the delta H of Na2O, which is negative 416. So what we're going to do is we're going to add up each side, multiply it out, and then arrange it in the proper order, because these are our reactants and these are our products, so we have to reverse it. So we have negative 832 taken from here minus 0 taken from here equals negative 832 kilojoules per mole. Number 2, 2 times 0 plus 2 times negative 285.8 yields 2 times negative 425.9 plus 0. Add up each side, multiply it out, put it in the proper order. This gives us negative 851.8 minus negative 571.6 equals negative 280.2 kilojoules per mole. So as you see, whenever I calculate the delta H of each reaction, I'm going to plug these units on the end, kilojoules per mole, and that is how we measure enthalpy. Moving on to number 3, which is our last equation that we must calculate the change in enthalpy for. We have 2, the coefficient taken from the initial equation, times 0, which is the change in enthalpy for each of those individual substances, plus negative 393.51 yields negative 416 plus 110.5. Add up each side, multiply it out, put it in the proper order again. So that gives us negative 526.5 minus negative 393.51 equals negative 132.99 kilojoules per mole. So just the easier way to visualize this, I set up all our changes in enthalpies for each of those three equations. So we have negative 832, negative 280, and negative 132.99. So this leaves us to conclude and to remind you again that reactions 2 and 3 include water and carbon dioxide. So equation number 2 involves H2O, and equation number 3 involves CO2. So equation number 1, where O2 is used in the extinguisher, there is much more energy being taken out of the sodium fire, therefore putting out that fire faster. So, to state my answer, the delta H in these two is sufficiently less than when O2 was used in reaction 1. Now this is why they are much less efficient, equations number 2 and 3, than O2, which is used in equation 1. There is much more energy being taken out when O2 is used in an extinguisher. So my next problem, number 39, involves intermolecular forces. So to make this easier when identifying which substance has which intermolecular force, I'm going to remind you all briefly of what each intermolecular force is and the ones that I will be working with. So first we have hydrogen bonding, and this occurs only when hydrogen is bonded directly to nitrogen, oxygen, or fluorine. Again, they may be in the same molecule, but if they are not directly bonded, then it is not a hydrogen bond. More hydrogen bonds makes a stronger IMF. Next up, we have dipole-dipole, and this occurs within a polar molecule. The greater the electronegativity, the stronger the intermolecular force. So, it does not matter what the charge of each individual atom is that is used to make up this molecule. It matters only the final charge of this molecule due to the configuration of the elements. So, those molecules or atoms used in the molecule may not be polar, but the molecule may be polar, giving it a dipole-dipole IMF. Next up is London dispersion forces, which is commonly shortened to LDF. So when you see LDF in my answers, it is London dispersion forces. This occurs whenever two molecules collide and electrons are temporarily displaced. More electrons to displace means a stronger intermolecular force. Now, all substances do have London dispersion forces. However, some only have London dispersion forces, so the substances labeled LDF only have LDF. The last one I will be going over is covalent networks. So covalent networks are substances that do not have intermolecular forces because each sample is one whole molecule. Examples of this are graphite, quartz, and diamond. So, set up next to each other to show a comparison between the strength of these intermolecular forces, we have LDF, dipole-dipole, hydrogen bonding, ionic bonds, and covalent bonds. So, as you can see, the one after each slightly overlaps the one before it, except for covalent bonds. This means, in any special case, that a very strong dipole-dipole bond may possibly be stronger than a hydrogen bond. However, this is very rare, and we will not encounter this in our following problem. But it's just nice to think about in case we ever do come in contact with that. Covalent bonding is also the strongest, and it would not be weaker than any bond, no matter the case. Whenever we see a covalent bond, it is always the strongest. Now on to page 488, number 39. It is asking us the highest boiling point of three substances. Now that means we are looking for the strongest intermolecular force. We have HBr, Kr, and Cl2. Now when determining intermolecular forces, it is important to draw out the Lewis structure of each of the substances to better identify them. So here, as you can see underneath, we have the according Lewis structures drawn out below it. HBr is dipole. Now, relatively, it may seem symmetrical. However, due to the valence electrons on Br, it creates a stronger charge on this side as opposed to that side, therefore making a polar molecule. Kr is LDF because it has no bonds and it gets its energy simply from its own electrons being displaced from movement. Cl2, this is LDF. It is completely proportional, therefore not dipole. It is not a hydrogen bond because there is no hydrogen involved. It is not an ionic bond, it is not one of our ions, and it is not a covalent bond. So this leaves us to conclude that because dipole is much stronger than LDF, HBr has the highest boiling point because its IMF is stronger than that of LDF. Moving on to B. This is asking us of the highest freezing point. Again, we are looking for the strongest IMF. We have H2O, NaCl, and HF. Once again, the Lewis structures are drawn out beneath each of the according formulas. And from that, we can identify which substance has which IMF. Here we see hydrogen bonded directly to an oxygen molecule, giving it a hydrogen bond. We have Na bonded to Cl, however it may be polar, it is an ionic bond because NaCl is an ion. HF, this has hydrogen bonding because we have hydrogen directly bonded to fluorine, therefore giving it the name hydrogen bonding. Now, if we can remember back to our order of IMFs, figuring out which one is stronger than the others, we can see that hydrogen bond is the second strongest bond, therefore making NaCl much stronger than H2O and HF, leaving us to conclude that NaCl has a higher freezing point than H2O and HF. Next up, with part C, we are looking for the lowest vapor pressure at 25 degrees Celsius. So that means from the given statement, we are looking for the strongest intermolecular force. Also, the highest boiling point. So we have Cl2, Br2, and I2. Drawn out the Lewis structures for each, and we can see that each of these have London dispersion forces. They are not polar, not covalent bonds, not ionic bonds, and not hydrogen bonds. So, when faced with a problem like this, where we have all London dispersion forces, we must then record the atomic numbers of each of the following substances. So from there, we can then use the periodic table to figure out which substance has the highest electronegativity. So working our way down the periodic table with I at atomic number 53, we can see that I has a much stronger electronegativity than Br and Cl, leaving us to conclude that I has the lowest vapor pressure at 25 degrees Celsius. Next off to D, we are looking for the lowest freezing point. Now in this case, we are looking for the weakest intermolecular force. We are presented with N2, CO, and CO2. Once again, drawing out the Lewis structures beneath each of the substances, we are left with LDF. This is completely symmetrical, so it is not dipole, there is no hydrogen involved, it is not a covalent bond, and it is not an ion. Next, we have CO. It is dipole-dipole. It is polar due to the extra pair of valence electrons on the oxygen molecule, giving it a greater charge on one side than the other. Then we have CO2 is also LDF. So right then and there,